So this is the first lesson in Chapter 11, and Chapter 11 is all about how to integrate complicated functions. So in the textbook, you'll see this nice list of integrals, these 9 integrals, which are some of the most common integrals that you're expected to recognize. So the first thing that I would recommend you do is try and learn all of these integrals. But what the point of this video is it's going to help you. If you forget one of these integrals, either how can you derive it or where can you find it in the formula book? Because unfortunately you don't get given something as nice and as easy to use as this in your formula book. So we're going to derive some of these integrals using the fact that differentiation and integration are inverse operations. So just to make sure we understand that concept, if we add the function 5 to the power x to the power of 5, if we differentiated x to the power of 5, we would get 5x to the power of 4. And because we know that integration is the opposite of differentiation, that tells you if we start with the function 5x to the power of 4 and we integrate it, then we're going to end up with x to the power of 5. And we could write that out formally as the integral of x to the power of 4. We're basically asking ourselves what the function differentiates to 5x to the power of 4, and that's x to the power of 5. So we're going to use this to derive some integrals. The first one is using the fact that we know how to differentiate e to the x. If we differentiate e to the x, you've seen in the previous chapter that just stays the same and you get e to the x. So that means that when you integrate e to the x, it stays the same, you get e to the x. So the integral of e to the x is just e to the x plus the constant of integration. So you're expected to remember that standard result. Another integral that you're expected to remember comes from the fact that you know how to differentiate log x, natural log of x. If you differentiate natural log of x, you get 1 over x. So that tells you that if you integrate 1 over x, you get natural log of x. So we could write that as another useful result. The integral of 1 over x is equal to ln of x plus c. Now there's one slight problem with this. If we try to substitute in a negative value of x into this formula, then we're going to take logs of a negative number, which isn't possible. So we don't need to go into too many reasons why this works, but you just need to remember that we're going to put a modulus symbol on either side of x, or an absolute value symbol, to ensure that x is always positive. So this is another formula that you're expected to remember. And we can also integrate the trig functions. Let's think about how to differentiate the trig functions. You've already seen that if you differentiate sine x, you get cos x, and if you differentiate cos x, you get minus sine x, and if you differentiate minus sine x, you get cos x. So if we were to put them in that order, if you go down this list, you're going to differentiate, and we know that integration is the opposite of differentiation, so if you go up this list, you're going to integrate. So for example, if you had wanted to integrate sine x with respect to x, we look at here, sine x on the diagram, we want to go up to integrate, and the diagram loops around. So we're going to loop around to minus cos x. Similarly, if we wanted to integrate minus sine x, then we would get cos x, we would move up in the diagram. Next, we'll look at where to find these equations 6 to 9 in your formula book, because you're actually given these in your formula book. So in the integration section of your formula book, you get told some function f of x and you get told its integral. So as you move from the left column to the right column, you're integrating. So that's fairly self-explanatory. So this tells us the integral of sec squared, tan, cot, cosec and sec. What is perhaps a little bit less obvious is if you look in the differentiation section, you actually get told a lot of integrals. So in the differentiation section, you get told a function f of x and its derivative. So as you move from the left column to the right column, you're differentiating in the differentiation section. So that tells us that if we move from the right column to the left column, we're doing the opposite of differentiation, which is integration. So for example, if we wanted to integrate sec squared of x, then we know that that is equal to tan x. because if you differentiate tan x, you get sec squared x. And it might be useful to note that with these two, you can swap around the minus symbol. So for example, if you wanted to integrate, well, let's say this line here tells us that if you integrate minus cosec squared x, so let's just put k equals 1 for now, then we get cot x. And the reason why is because if you differentiate cot x, you get minus cosec squared x. Well, it's useful to know that you can swap around the minus symbol. So if you times through by minus 1, you're going to get the integral of cosec squared x is equal to minus cot x plus c. Something to be careful of with these integrals is you can't replace x with any function of x. So for example, if you were integrating e to the 3x, you might be tempted to say, well, that's just going to be equal to, if you take this formula here and replace x with 3x, you might be tempted to say, well, that's just going to be equal to e to the 3x plus c. Well, you can convince yourself that this isn't true, because if you differentiated e to the 3x, you would actually get 3 e to the 3x, not just e to the 3x. So this would be incorrect. So these integrals that we've written here only work for the time being if we've got x. But we will deal later on with this problem of what happens if we did have 3x there.